OWASP API Security Top 10. The Data Leak Trio. Imagine an app that shows you your own profile, just your username and a little profile picture. Simple enough. But behind the scenes, when that app asks the server for your profile, what if the server actually sends back far more than a username and a picture? Your password's encrypted hash, your social security number, even private internal notes about your account. And the app just quietly ignores all of that extra information when it draws the screen? That's the core idea behind this whole category of risk. The screen looks completely fine, but the actual data traveling between server and app contains far more than what's displayed. How it actually works in depth, let's name the 3 specific patterns in this group because each is slightly different. The first is called BOLA, Broken Object Level Authorization, which we actually covered back in week 1 as Broken Access Control. As a quick refresher in this new context, the API returns data without properly checking whether the specific thing being requested actually belongs to the person requesting it. The second is Broken Authentication, also covered conceptually in week 1, but here applied specifically to APIs. The API itself can't reliably verify who is calling it, separate from whatever the website's login page might show. The third is new, excessive data exposure. This happens when an API sends back every field from its internal data model and simply trusts the front-end application to politely only display the fields it needs. Picture requesting a single user's profile and the response includes their username and avatar, which the app displays, but also includes their password hash, their social security number, and private internal account notes, which the app never shows on screen, but which absolutely exist in the raw response, fully readable by anyone who opens their browser's developer tools and looks at the actual network traffic. Its role in the field, these 3 sit at the very top of API security work because they share a common root cause. APIs are quick to build by simply returning whatever an internal database query happens to produce, rather than deliberately constructing a minimal, purpose-built response. If you move into API security work, reviewing endpoints for oversharing exactly like this becomes one of your most frequent bread-and-butter tasks, and it requires nothing more exotic than opening a browser's network tab and actually reading what comes back, field by field. Why it matters. What makes this category particularly dangerous is its invisibility. A broken web page announces itself. Something looks wrong. A feature crashes. An API quietly returning 10 extra sensitive fields announces nothing at all. The application functions perfectly. Nothing crashes. The only way this gets caught is if someone deliberately inspects the raw response rather than just the rendered screen, which is precisely the habit this entire course is trying to build in you. Why this trio matters most. Think about a busy commercial kitchen that prepares 100 different dishes, but uses one master tray to carry every single order out to the dining room, fully loaded with everything that particular dish's recipe touches, including ingredients the customer never actually ordered or sees on their plate. The waiter simply removes the visible parts onto the customer's plate and assumes nobody looks at what's still sitting on the tray underneath. How it actually works in depth. There's a specific structural reason these 3 vulnerabilities dominate real breach statistics, rather than being rare edge cases. APIs are typically built fast, by reusing one shared internal data structure to answer many different kinds of requests. A single user object used everywhere a user needs to be represented. The convenient part of this pattern is also the dangerous part. That one shared object often contains every field the system has ever needed for any internal purpose, including fields no external app should ever see. Compounding this, developer testing habits typically focus entirely on the rendered screen. Does the page look correct? Does the right name and picture show up? And rarely involve opening the raw network panel to manually inspect what was actually transmitted underneath that screen. Its role in the field. This is genuinely where API security engineers spend the bulk of their actual working hours. Not on exotic, novel attacks, but on this exact, repeated pattern across dozens or hundreds of endpoints in a typical enterprise application. If you're building toward this role, get comfortable with the habit of opening Postman or browser dev tools and reading every single field in a raw API response, not just the ones the screen happens to display. Why it matters. The fix, fortunately, is consistent across all 3 of these vulnerabilities, which makes them very learnable as a unified skill rather than 3 separate things to memorize. Build a strict, deliberate response shape for every endpoint, an explicit allow list of exactly which fields should go out, rather than simply hiding unwanted fields in the user interface while they remain present and exposed in the underlying data. Once you internalize this one habit, you've effectively covered the most common category of API vulnerability in the entire industry. OWASP API Security Top 10. Abuse and defaults. Imagine a busy shop with an open front door and absolutely no limit on how many times someone can try a key in the lock. They could stand there all day trying thousands of different keys with no consequence, because nobody's watching the door or saying, "That's enough attempts. Please leave." That's the essence of having no rate limiting. How it actually works in depth. This group covers 3 different but related failures. No rate limiting means an API never tracks or restricts how frequently a particular user or device can call it. Without this control, anything that requires repeated guessing, like trying many passwords, becomes fully automatable. A script can attempt 10,000 different password guesses against one account in a single minute, with the server never once saying, "You've tried too many times." Mass assignment is a subtler, code-level problem. Imagine a form on a website that only displays 2 editable fields, your name and your email. The form looks simple, and the front-end developer reasonably assumes only those 2 fields can ever be changed. But what if, instead of using the website's actual form, someone sends a request directly to the underlying API and simply adds an extra field the form never showed? Say, a field called role, set to admin. If the backend code blindly accepts and saves every field it receives, without explicitly checking which fields are actually allowed to be updated this way, that user just silently promoted themselves to administrator. Security misconfiguration in the API context specifically mirrors what we covered generally in week 1, but shows up here as things like API documentation left publicly accessible that reveals internal endpoint structures, or error messages that return overly detailed technical information instead of a generic failure message. Its role in the field. These 3 are specifically what automated security scanning tools, the DST, and API-specific scanners used in DevSecOps pipelines are typically configured to check first, because they're mechanically detectable. Does this endpoint have a rate limit? Does this endpoint accept unexpected fields? Is documentation exposed publicly? If you move into a DevSecOps adjacent role, configuring and tuning exactly these checks in an automated pipeline becomes routine work. Why it matters? What separates this group from many other vulnerabilities is how directly and immediately they scale. A single missing field validation check doesn't just expose one record. It can mean literally any user on the platform can grant themselves administrator access, instantly and repeatedly. A missing rate limit doesn't just allow one extra guess. It allows unlimited automated guessing forever, until someone notices and fixes it. Why abuse and defaults matter. Picture a single unlocked side door on an otherwise well-secured building. It doesn't matter how strong the front door's lock is. If there's one quiet door around back that nobody thought to secure, and someone finds it, they now have unrestricted, repeated access for as long as that door stays open, completely bypassing every other security measure in the building. How it actually works in depth. Let's walk through exactly why these particular flaws are considered so severe, using the same 2 examples with their actual scaling math made explicit. With no rate limiting, a single leaked or guessed password becomes the starting point for an automated script trying 10,000 different password combinations every single minute, against potentially every account on the platform simultaneously, not just one. With mass assignment, a single missing line of validation code becomes the difference between every user account on this platform is exactly as privileged as it should be, and any user, at any time, can quietly elevate themselves to the highest privilege level that exists in the system, simply by sending one slightly modified request. Its role in the field. In real AppSec and DevSecOps work, this is precisely why checklist-style, repeatable verification matters so much, and why the role isn't really about being clever or creative most of the time. It's about being thorough and consistent every single time across every endpoint without exception. This consistency over cleverness quality is genuinely good news if you've ever doubted whether you're creative enough for security work. This category specifically rewards discipline, not cleverness. Why it matters. The underlying fix for both of these issues is the same simple philosophy. Be explicit, never implicit. Explicitly define and enforce a request rate limit, rather than assuming abuse probably won't happen. Explicitly allow list which fields a user is permitted to update, rather than trusting that nobody will think to send an extra field. This single mental habit, say exactly what's allowed, rather than only blocking what you've already thought of, is one of the most transferable lessons in this entire course. Authentication fundamentals. Think about checking into a hotel. You show your ID once at the front desk to prove who you are. After that, the hotel doesn't ask you to show your ID again every single time you walk past the lobby. Instead, they hand you a keycard, a temporary token that represents this person already proved who they are, and every door simply checks the keycard from that point forward. How it actually works in depth, that hotel keycard is functionally identical to what happens technically during authentication. When you log into a website or app, your browser sends your email and password to the server one single time. The server checks that against its records, and if it matches, the server doesn't ask you to resend your password on every subsequent click. That would be both slow and would mean transmitting your sensitive password constantly, increasing the chance it gets intercepted. Instead, the server generates something called a token, essentially a temporary, cryptographically signed piece of proof that says, this specific browser already proved its identity, and here's a way to verify that claim without redoing the whole login process. From that point forward, every subsequent request, viewing your orders, updating your profile, simply includes this token instead of your password, typically inside something called an authorization header. Its role in the field authentication sits at the very front gate of essentially every security review you'll ever do, because almost every other security control implicitly assumes authentication already works correctly. When a security engineer starts reviewing a new application, checking how login and tokens work is almost always one of the first things examined, before moving on to anything more specific. Why it matters given your specific background in API integrations, this is genuinely your highest leverage topic in this entire course. You've spent years connecting systems together, and every single one of those integrations almost certainly involved some form of authentication, whether you were thinking about it explicitly as security or not. Reframing that existing, deep experience through this lens is less about learning something brand new and more about recognizing a skill you've already been quietly building for years. Why Auth is the foundation. Imagine a security guard at a building's front entrance who diligently checks every single visitor's ID, but the building's internal floor directory, the one that decides who's allowed into which specific room, has no way of actually knowing who that guard just let in. Every internal door is essentially guessing at identity, based on nothing solid. How it actually works in depth, let's trace the dependency chain explicitly, because this is the part that makes authentication uniquely foundational rather than just one item on a longer list. Access control checks, the kind we discussed back in week 1 with the order ID example, fundamentally ask, is this specific person allowed to see this specific piece of data? But notice that question already assumes something prior, that the system correctly and reliably knows who this person actually is. If authentication is broken, that assumed foundation simply isn't there. Rate limiting similarly asks, has this particular person already tried too many times? But again, that requires confidently knowing it really is the same person making repeated attempts, rather than, say, an attacker freely generating brand new identities to sidestep any per-person limit entirely. Its role in the field, this is why, in any real security assessment, broken authentication issues are treated as having outsized severity compared to many other findings. Not necessarily because the authentication bug itself is dramatic, but because of everything downstream that silently inherits its uncertainty. A security engineer who finds a broken authentication issue knows, immediately, that every other security control in that system needs to be re-examined under the assumption that user identity itself might not be trustworthy. Why it matters. If you remember just one structural fact from this entire topic, make it this: authentication isn't simply one item on a list of things to check. It's the load-bearing wall that every other security control is built on top of. Get comfortable identifying weak authentication first before diving into anything else, because finding it early reframes how seriously every other finding in that same system should be taken. OAuth2 and JWT deep dive. You've almost certainly clicked a sign in with Google or sign in with Facebook button on some website before. Have you ever wondered why that website never actually asks for your Google password directly? That entire mechanism, letting one application vouch for your identity to a completely different application, without ever sharing your actual password between them, is what OAuth2 was specifically designed to solve. How it actually works in depth, let's walk through the real sequence of what happens, step by step, the next time you click that button. First, the website you're visiting, let's call it Site X, redirects your browser away from itself, over to Google's own login page. This redirect is important. You are now interacting directly with Google, not with Site X. Second, you log in using your actual Google credentials, but you're typing that password into a Google-owned page, not into SiteX at all. SiteX never sees, receives, or stores that password in any form. Third, Google explicitly asks you a permission question. SiteX is requesting access to see your name and email address. Do you want to allow this? This step matters because it's Google, not SiteX, defining and limiting exactly what's being shared. Fourth, once you approve, Google sends SiteX something called a token, not your password, just a piece of verified proof containing the specific limited information you agreed to share. SiteX now reliably knows who you are, without that knowledge ever requiring access to your actual login credentials. Its role in the field OAuth2 has become the standard mechanism behind the vast majority of login with buttons across the modern internet, and it also underlies how many back-end systems and APIs authenticate with each other automatically, without any human login step at all. If you work in API integrations, which you already do, you very likely implemented some version of this flow already, even if you were thinking of it simply as connecting to the Payment Gateway's API, rather than explicitly as OAuth2. Why it matters. The elegance of this design is exactly why it matters. It lets two systems establish trust without ever needing to share a long-term secret like a password between them. If SiteX were ever breached, attackers still wouldn't gain your actual Google password, because SiteX genuinely never possessed it in the first place. That containment of damage by design is the entire point. Inside a JWT token, imagine a wax-sealed letter from a king, back in a much older era. Anyone could read the contents of the letter just by opening it. The seal wasn't there to hide the message. The seal's real purpose was to prove the letter genuinely came from the king and hadn't been altered along the way. If the wax seal were ever broken or tampered with, everyone would immediately know the letter could no longer be trusted. How it actually works in depth. A JWT, short for JSON Web Token, and pronounced JWT, works on exactly the same principle. A JWT is made of three distinct parts, separated by periods, that together look like one long string of text: a header, a payload, and a signature. The payload, sometimes called the claims, contains the actual readable information, things like a user's ID number, their assigned role, and an expiration timestamp telling the system when this token should stop being considered valid. Importantly, this payload is typically just encoded, not encrypted, meaning anyone can technically read it, similar to how anyone could read that sealed letter once opened. The signature is the wax seal. It's generated using a secret key that only the legitimate server possesses, and it mathematically proves that the payload hasn't been altered since the token was originally created. If even one character of the payload were changed by an attacker, say, quietly editing their role from customer to admin, the signature would no longer mathematically match, and any properly built server would immediately reject that tampered token. Its role in the field. JWTs have become the single most common token format across modern APIs, which means that as an AppSec or API security engineer, you'll encounter and need to evaluate them constantly, practically as a routine daily task. 3 specific questions become your standard checklist whenever you encounter one. Is the signature actually being verified on the server side, rather than just trusted blindly? Is the expiration timestamp actually being enforced and checked, rather than just present but ignored? And can any of the claims inside, particularly something sensitive like a role or permission level, be edited or influenced by the user themselves in ways the server doesn't expect? Why it matters. A surprising number of real-world vulnerabilities trace back to servers that accept a JWT's claims as automatically trustworthy, without ever actually verifying that signature server-side, effectively trusting the contents of that sealed letter without ever checking whether the seal was real or had been tampered with. Understanding this one mechanism deeply will let you immediately spot one of the more subtle but genuinely common categories of real-world API vulnerabilities. HTTP fundamentals for security. Imagine asking a librarian for a specific book. There's an important difference between the librarian saying, "That book doesn't exist in our entire catalog," versus the librarian saying, "That book exists, but it's restricted, and you're not permitted to check it out." Both responses mean you don't get the book right now, but they reveal very different amounts of information about what actually exists in that library. How it actually works. In-depth. HTTP status codes are the standardized 3-digit numbers a server sends back with every single response, and a handful of them carry direct security significance. The number 401 specifically means unauthorized, which, despite the somewhat confusing name, actually means you are not currently authenticated. Please log in. The number 403 means forbidden, meaning you are authenticated. The server does know who you are, but you specifically are not permitted to access this particular resource. Here's where this becomes a genuine security consideration, not just technical trivia. Imagine you request someone else's order using a URL like /orders/9999, an order that doesn't belong to you. If the server responds with a 404, not found, that response is quietly informative to an attacker. It confirms that, at minimum, order ID 9999 doesn't exist as a record at all, which can help an attacker iterate through ID numbers to map out exactly which ones are real versus which are simply unused, purely by watching which return 404 versus something else. A better response in this exact scenario is a 403, forbidden, which reveals nothing whatsoever about whether order 9999 actually exists or not. It simply states, neutrally, that this particular request isn't permitted, full stop. Its role in the field. Reviewing exactly which status codes an API returns under different conditions is a fast, genuinely high-value check that security engineers run constantly, precisely because it requires no special tooling beyond something you already use daily, Postman, or even just a browser's network tab, and yet it reveals real, exploitable information leakage patterns that are very easy for developers to overlook entirely. Why it matters. This category of issue is subtle specifically because nothing is broken in the traditional sense. The API still functions correctly, no error occurs, no crash happens. The conversation between server and user is just slightly too informative, more talkative than it strictly needs to be, and that small excessive information becomes a tool an attacker can use to map out a system's internals long before attempting any more direct or aggressive attack. Why headers and cookies matter. Imagine a wristband at a venue that proves you've already paid for entry. Now imagine 3 small, almost trivial-seeming printed details on that same wristband. A notice that says it can only be photographed by venue staff, not the general public. A separate notice that it's only valid at this specific venue, not any other building down the street, and a third notice that it can't be transferred or used by anyone other than the original wearer it was issued to. None of these details change the basic wristband mechanism, but each one closes off a specific, real way the wristband could otherwise be misused or copied. How it actually works in depth. That's essentially what cookie security flags accomplish for browser-stored session tokens. A cookie is a small piece of data, like that session token we discussed earlier, that a browser automatically stores and resends with future requests. The HTTP-only flag tells the browser, don't allow any JavaScript running on the page to read this particular cookie's value at all. This single flag is specifically designed to block a very common attack where malicious script, injected through some other vulnerability, attempts to directly read and steal a user's session token. The secure flag tells the browser, only ever send this cookie over an encrypted HTTPS connection, never over plain, unencrypted HTTP. This single flag prevents the token from being exposed in plain, readable text if it ever happens to travel over an insecure network connection. The same site flag controls whether this cookie gets automatically sent along when a request originates from a different website entirely. Setting this to strict helps prevent a category of attack where a malicious site tries to trick a user's own browser into making unwanted requests using their existing, valid session. Its role in the field. Reviewing these exact header and cookie flags is one of the fastest possible checks in any security assessment. And notably, you can practice this right now, today, using Postman, a tool you already use constantly in your current integration work. Simply inspect the response headers the next time you're testing any login flow, and actively look for whether these 3 flags are actually present. Why it matters. Each of these 3 small flags closes off one specific, well-documented, and genuinely common real-world attack path. None of them require complex code changes to implement, they're typically a single configuration line, yet a surprising number of real production systems are still missing one or more of them, often simply because nobody on the team happened to specifically check for their presence. ORS explained. Imagine a strict bouncer standing at the door of an exclusive club, whose entire job is checking whether other club staff members, specifically, are allowed to walk in. Now here's the important and often missed detail. That bouncer only ever checks people arriving in another club's uniform. Someone walking in through a completely different entrance, say a delivery door at the back used by trucks and direct deliveries, never encounters that bouncer at all. CORS works on exactly the same principle, and missing this distinction is the single most common point of confusion about what it actually protects. How it actually works in depth. CORS, which stands for Cross-Origin Resource Sharing, is fundamentally a rule enforced by web browsers, specifically governing which website's own JavaScript code is allowed to make requests to your API directly from within a user's browser. Here's a concrete working example. Suppose your API explicitly sets a CORS configuration allowing requests only from https://yourshop.com. This setting means that JavaScript code running on yourshop.com, loaded inside a user's browser, is permitted to successfully call your API. If JavaScript running on some unrelated site, evilsite.com, attempts that exact same call from inside a user's browser, the browser itself actively blocks that specific request before it ever meaningfully reaches your server. But, and this is the critical, frequently misunderstood part, this protection applies specifically and only to requests originating from JavaScript running inside a web browser. It does absolutely nothing to stop someone using Postman directly, or a simple command line tool like curl, or one server calling another server directly through code, completely outside any browser context. None of those paths are browsers, so none of them are bound by CORS rules in any way whatsoever. Its role in the field. Understanding this distinction precisely is what separates a surface-level, checklist understanding of CORS from genuine practical competence with it. Many developers, quite understandably, assume that a properly configured CORS policy functions as their API's actual security boundary, when in reality, it only meaningfully restricts one single category of caller, browser-based JavaScript. Every API still needs its own independent authentication and access control, regardless of whatever CORS policy happens to be configured alongside it. Why it matters. If you walk away from this topic believing my CORS configuration secures my API, that single misunderstanding alone can lead directly to a false sense of security, while every actual authentication and access control vulnerability remains completely unaffected by however carefully CORS itself happens to be configured. Why CORS mistakes happen. Picture that same bouncer from before, except now imagine someone hands him a sign reading, "Everyone is on the approved list," while he's simultaneously still handing out a special all-access wristband to every single person who walks past him, no matter who they claim to be. The combination is what creates genuine, severe risk, not just the open guest list alone, but that open list paired specifically with a powerful, trusted credential being issued indiscriminately to absolutely everyone. How it actually works in depth. The single most common and consequential CORS misconfiguration is setting the access control allow origin header to a literal asterisk character, meaning, quite literally, any website whatsoever is allowed to call this API directly from within a user's browser. On its own, that setting alone is a real but fairly limited risk. It mainly just means data which isn't otherwise protected by genuine authentication could potentially be more broadly readable by other sites than originally intended. The danger escalates sharply, however, when that same wide-open asterisk setting is combined with a second setting. Access control allow credentials set explicitly to true. This particular combination effectively means that any website on the entire internet can make a request to your API using a victim's own active, currently logged-in session cookies, automatically, silently, the instant that victim simply visits a malicious page while still logged into your legitimate site in another browser tab. The malicious site never needs to actually steal the victim's password or session token directly. It simply rides along on the browser's own behavior of automatically attaching existing cookies to outgoing requests. Its role in the field. Reviewing CORS configuration for exactly this specific dangerous combination is a completely standard line item on almost every API security checklist that exists, precisely because it's a single, narrow setting combination that's surprisingly easy to misconfigure, especially under normal development pressure, and yet it carries genuinely severe consequences when it slips through unnoticed. Why it matters. The fix here is refreshingly simple and concrete. Never combine a wildcard asterisk origin setting with credentials enabled. Instead, explicitly list the exact, specific domains that are genuinely trusted to make these kinds of authenticated, credentialed requests. This is a small, one-line configuration change with an outsized, meaningful impact on your application's actual real-world security posture.